Alright, we're coming into our last video. This is technically officially part 3 of the video, and we're going to actually deal with what's called LeChatleier's Principle today. Now, the goal is, without notes, that you're able to apply LeChatleier's Principle to determine the equilibrium shift when stress is applied to a reaction. Overall, our goal is to understand what happens when we have this reaction that's at equilibrium and we change something about it. We stress the system, as we would call it. What's actually is going to happen to the reaction? Which way will it shift to adjust? Because the goal is to get back to that equilibrium point. So let's go ahead and take a look at it. Now, Le Chatelier's principle is this. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. The same thing happens to us. When we're comfortable doing whatever, maybe we're laying on the couch and somebody decides that they want to come and sit on the couch with us. We may not be able to stretch out the same way that we were, or have everything laid out the way that we want to. But we would try to do whatever we can so that even though that other person has come into the situation, into the system, that it doesn't change our comfort level and our ability to do what it was that we were going to do. Now, the reactions do the same thing. Now, if I change certain things, the first thing we're going to talk about is concentration. If I change the concentration of some kind of component of one of the reactants or products, it's going to shift away from that change. What do I mean? If I add in, say if this is my reaction, H2 plus O2 yields H2O. If I'm looking at this reaction and I add in, say, hydrogen gas, the reaction is going to shift in a direction that will produce more water. Now, the same thing is going to happen if I take away or reduce the concentration of a reactant. Then it's going to shift towards that direction so that it will be able to replenish or make up that difference. Now, the second thing that we want to look at is overall temperature. And I can sort of take my time here because you'll notice that this part of the video is actually kind of short. But for temperature, if I change it, it's going to shift in the way of the reaction that is endothermic. Now, this is where that delta H part comes in. When we have delta H as positive overall, if I was to increase the temperature, that means that there's more energy for those particles that are going to react, that are going to collide, that are going to be oriented in the right way to collide and to make that reaction go on. The reaction will shift in a direction that will use up that energy as much as possible. Now, back to the question I asked a little bit last week when I asked, in an exothermic reaction, is energy a reactant or a product? Well, endothermic energy is a reactant. Exothermic, again, energy is a product. It's released, it's gone at the end. So that means that the overall reaction is, the forward reaction, is exothermic, and I add in heat, that means that it's going to shift back towards the left, because that will be the way that would use up that extra energy, that excess energy, and be used as a reactant. Now, the other change that I can make is I can change the pressure. This can happen in a couple of ways. First off, if I increase the pressure, the system will shift away from the added gases component. I know that sounds a little strange, but let's go back to it. If a component is removed, the opposite effect occurs. So if I have Cl2 plus PCl3 coming together, it's going to form PCl5. If I increase the pressure, I believe this is, yeah, we're balanced. If I increase the pressure, it's going to shift away from the added gaseous component. That could be by concentration. If I increase the amount of PCl5, it's going to actually shift back towards our reactants, just as we talked about before. If I remove it, same things we talked about. Now, if I add in an inert gas, it doesn't affect the equilibrium position at all. So if I was to add in a noble gas, say like helium, for whatever reason, nothing changes about how the reaction proceeds. We have no issues as far as it affecting the reaction, the equilibrium position or constant. Now, last but not least, if I decrease the volume, it's going to shift towards the side that has fewer moles of gas. So let me go ahead and back and erase this, erase my helium because that's not necessary. When I look at this overall reaction, on my left side I have 2 moles of gas, where on my right side I only have 1 mole. So if I decrease the volume of the vessel where the reaction is taking place, the reaction is going to shift to make more of our product. It's less space, so you're going to have more collisions, and with those collisions you're also going to have more energy and so forth. Same as if I increase the volume, it's actually going to slow down, and the opposite is actually going to take effect. We're going to see more of it breaking down and going into forming the reactants. Now, I told you this part was actually going to go very, very quick. So, do a quick recap. Le principle just says that if we adjust or if we interrupt the equilibrium process, the reaction is going to try to get back to it any way that it can. And we gave a couple of different ways, looking at concentration, looking at changing the temperature, and looking at changing the amount of pressure in the system and how that will affect. Now, our time in class is really going to be spent on understanding what those different shifts are going to be or what will cause those different shifts. Now, take a moment and evaluate. Where are you? Do you understand? Do you not? If you are lost, write down your questions. Please write down your questions so we can get them answered and make sure you understand what's going on in class. Take your time, and I will see you again in class where we'll continue this discussion.